Good morning, everybody. I would also like to thank Thorsten and his team for the wonderful organization here. I know it's a lot of work, and I particularly appreciate the poster session, which is very nice. Oops. Excuse me for this. In my talk, I will focus on three issues. First, I will provide an example how the past can be used to compare with the current situation, then how paleodata can be used to constrain an Earth system parameters, in this case the carbon cycle climate feedback, by looking at data of the last millennium, reconstructions of temperature and CO₂. And in the third example, looking at Holocene CO₂ and C13 evolution, I will kind of try to see how we can use paleodata to actually demonstrate our system understanding. What about rates of climate change? There is a lot of discussion that current atmospheric CO₂, methane and N2O concentrations are high, indeed higher than measured in the ice cores over the past 800 kilo years, and also higher than, as we will see later, over the past 2 million years and even further back in time. Another issue is how fast the changes are, and rates of climate change co-determine the severity of impacts on the socioeconomic as well as on the natural system. So it might be important to compare rates of climate change from the past with what's going on today. However, there is one difficulty, and that is proxy data of past temperature are quite uncertain and sparse. But we have accurate records of past greenhouse gas concentrations available, and the greenhouse gases are forcing climate to change. And if we follow this logic, then we may actually use reconstructions of climate forcing as a proxy of climate change. And for addressing rates of change in greenhouse gas concentration, we need to take into account two issues. First is when the atmospheric signal, let's say of CO₂ or methane, gets enclosed and the air bubbles in the ice core, then this enclosure process acts as a smoothing process. The atmospheric signal gets smoothed, and we have to consider this smoothing. Second issue is if we deal with different greenhouse gases or forcing agents or solar forcing or volcanic forcing, we need to define a common metric, and for this one can use the well-established metric of radiative forcing. So the first question we might ask is if we have these reconstructions of greenhouse gases in the ice cores, and we might wonder whether we would detect in an ice core the anthropogenic CO₂ and methane peak as measured over the last 200 years by high-resolution ice core and also by direct atmospheric measurements. However, in the low-resolution ice core typically used to reconstruct greenhouse gas concentrations over longer timescale deep into the past, then low accumulation sites are used where the age distribution of the air enclosed in the ice is several centuries. So we are looking here at the results from a Bern diffusion and enclosure model where, in this case, methane, I know Jerome likes this gas very much. You can see here the rise from 700 ppm up to 1800 ppm as indicated by the black line. That's the direct atmospheric signal. And then how this signal would be recorded in the ice at Antarctica in the epicadome sea core for conditions that are typical during the last transition. And what you can see is that the height of the peak is greatly reduced, and obviously also the rate of increase is greatly reduced compared to the original peak. So to infer rates of change from the greenhouse gas records here, as an example, I plot the methane concentrations over the past 20,000 years. So with the low values during the glacial periods of about 300–400 ppb, then the increase in the Berlin-Alleröd, the Younger Dryas fluctuations, and then the slow evolution during the Holocene. And at the right end, you see the rapid anthropogenic rise. And we can draw a spline fit through this data to make this record a continuous one, and then compute the rates of change from this spline fit. And that's what we get here if we do this for different gases and for the combined radiative forcing of these gases. You see the records are really very flat, and then we have at the end this rapid rise in the rate of change, this acceleration of the CO₂ increase. And if we take into account the smoothing of the anthropogenic CO₂ peak, that's indicated here by this black arrow, you see that the magnitude of order 4 watts per square meter and century is greatly reduced to this level here, but it's still considerably higher than anything else that is recorded in the ice core over the past 20,000 years. And the same holds true for CO₂, as well as for methane. For methane, we don't actually need to take this smoothing into consideration, as there are high-resolution records from Greenland, where the smoothing is not as large. So this leads us to the conclusion, and this was also entering the last IPCC assessment report, that the rate of increase in the combined radiative forcing from these greenhouse gases is very likely unprecedented during the last 20,000 years. And we also compared rates of change in solar and volcanic forcing on the decadal and century timescale of the last millennium, and could show that the current anthropogenic rate of change in forcing is higher than this natural component. So this kind of implies that climate change is really underway at high speed at the moment. So let's now change subject and discuss another issue, and that is there's a lot of talk about the magnitude of the carbon cycle climate feedback. We know that the carbon cycle processes are sensitive to climate change. Let's say CO₂ solubility in the water depends on temperature, or primary productivity on land depends on precipitation and temperature and so forth. And so there is a good justification that actually the carbon cycle will react to climate change and perhaps amplify the ongoing global warming. The question is, however, how big this feedback is. There has been various publications in the literature, and most recently by Cox and Jones, who suggested a very high amplification based on CO₂ and temperature reconstruction data of the Maunder minimum period. And they came up that for each degree of global mean surface temperature warming of 1 Celsius, there will be an additional 40 ppm in the atmosphere or so, whereas other assessment came up with lower number. And so the question is there a strong or is there a weak warming amplification? It's also clear that the last millennium is not the perfect analog for the future, as the changes in climate were relatively modest compared to what we expect, but at least these numbers are kind of important if we want to judge how good the models are, at least in representing the current situation, the last millennium and the industrial period, and perhaps then also for the future. So here is just a review of a few papers that show different ranges for this carbon cycle climate feedback. So some suggest it's between 4 and 60 ppm per degree warming, and others suggest it could be much higher, up to 40 ppm per Celsius. Why is this discrepancies in the different assessments? Here, plotted is temperature and CO₂ evolution as reconstructed for the last millennium. In the top panel, you see the meanwhile well-known reconstructions done by the different groups. You see there's these different spaghetti lines with differences in the magnitude of the fluctuations. And but what's kind of typical is that the records show temperature fluctuations over the whole millennium. In contrast, in the lower panel, you see the fluctuations in the CO₂ as measured on the low dome ice core. It's a high accumulation ice core in Antarctica, and also as measured at the South Pole and another ice core. And what you can see in CO₂, there is a dip in the concentration in the 17th and 18th century, and then in the early part of the millennium, the CO₂ concentration remains fairly constant. And if we consider these two periods, it is clear that if somebody takes just this period here from the records and combines it with a suitable temperature reconstruction up here, then you will naturally get a relatively large number for this carbon cycle climate feedback. That is, the CO₂ here is responding strongly to the temperature signal up here. Whereas if you look in this period here, you will rather expect a relatively low carbon cycle feedback. And of course, there are different reconstructions and so forth. So the goal forward is somehow to avoid a too subjective judgment, and this was done here by David Frank at Birmensdorf at the Institute for Forestry Research, and he actually recalibrated all this temperature reconstruction with respect to different instrumental target to compile an ensemble of about 500 temperature histories, and then he produced an ensemble of about 200,000 estimates for the carbon cycle climate feedback by combining the different temperature records and CO₂ records, looking at different analysis periods, different smoothing of the records, and so forth. I don't want to go into detail. The goal of this work done by David Frank is really to minimize the influence of subjective judgments. And with this probabilistic approach, we're coming up with this figure here. You see three colors, a red and a blue one, and then also the combined or the black color. The red color is for all the estimates that were taken during the early part of the millennium. So we have very small feedbacks to medium strength of the feedbacks, and the blue colors are for all the estimates taken from the second half of the millennium, where there are some possibilities for very high feedbacks implied in the records, as for example estimated by Cox and Jones. But as these feedbacks need to be the same during both periods, we may look here at the combined probability density function and see then that the mean feedback is somewhere between 3 and 14 ppm per degree warming. So the combined CO₂ and temperature variations, as assessed here in a probabilistic way, suggest that for modest temperature changes up to 1 degree Celsius, the feedback strength is in the order between 4 and 13 ppm Celsius, and that's quite comparable to most of the C4 models when those models are regressed over the industrial period, or the results of the model are regressed over the industrial period. So another conclusion is then that the recent high estimates brought forward by Cox and Jones are not compatible with the entire record and are likely a result of cherry picking just a particular period in the entire record. Okay, so let's again change subject, and let's use paleo data to demonstrate that we have some system understanding and look at the Holocene CO₂ variation. That's a problem that is with us since about 10 years or so. You can see here the CO₂ record published by Indermühle in 1999 that shows a slight decrease in CO2 at the big early Holocene and then an increase of about 20 ppm during the late Holocene. And the big question is what caused these fluctuations and what are the responsible mechanisms? There are conflicting hypotheses in the literature, and a wide range of proposed mechanisms is on the table that might be responsible for the changes. When we published the CO2 record in 1999, and we had also a few preliminary delta C13 data at hand. Based on this C13 data, the suggestion was that it's changes in terrestrial carbon storage in combination with sea surface temperature changes and perhaps changes in the calcite cycle. And this assessment has provoked further study. Bröker has challenged that, said the C13 data are not really good quality, at least those that we had back then, and he suggested that calcium carbonate sediment compensation in response to a terrestrial uptake during the transition. So the idea is that there is a forest regrowth and soil buildup during the transition, during the warming, and this kind of provokes a millennium scale adjustment process in the caput system, which tends to rise CO2 during the Holocene. Andy Richwell and others suggested that coral reef buildup contributed greatly to the observed fluctuation. They suggested something like a change in the order of 20 to 40 ppm, so much higher than actually reconstructed, and a radically different view was taken by Bill Ruddiman, who suggested that human land use caused the CO2 rise and prevented us from plunging into a new ice age. And then there are other works, in particular I would highlight Viktor Brovkin, who recently showed that based on both data and so SST reconstructions and modeling results, that changes in sea surface temperature are very likely not important for driving CO2 changes over the Holocene. But still, there are many different hypotheses on the table, and so what we want here is actually an accurate and also reliable constraint to pin that down a bit better. And it's good that this constraint have become available in the form of a new high precision delta C13 record. That record is shown here in the upper part of the plot, and you can see a increase in delta C13 of about 0.2 per mil at the early part of the Holocene. Actually, here I plotted the timescale in the wrong direction to serve PEC. And then in the late Holocene, during the time when we see the CO2 rise, the delta C13 signal remains really flat. And the confidence in this record is quite high. And why is this the case? You see here red and blue dots, and this dot or these points actually represent results from two completely independent measuring systems. One is taken with a cracker extraction and gas separation, and the other one is taken using a sublimation method to get the air out from the ice. So this constraint could be used to come at grips what's going on in this very complex carbon cycle. We have here an overview of the carbon cycle with vegetation, soils, with the ocean, with ocean sediments, with the atmosphere, and between those reservoirs are different fluxes going on, and within each reservoir a multitude of processes, and it's also clear that the fluxes and processes vary in space and time. So just to caveat a bit that one record right C13 may not telling the whole story, but it could be very useful. And the way it is useful is simplified here by adding this isotopic signature to the different reservoirs. And so by oversimplifying the story a bit, I could say, okay, we have organic material in vegetation and soil or in marine organic matter that is depleted in delta C13. Then we have the inorganic carbon in the ocean in the form of dissolved inorganic carbon, or in the form of calcite sediments, or in the form of coral reefs, and this have an isotopic signal that is close to the reference ratio, and the atmosphere is somewhere in between those source regions, so to say. So if we add isotopes from one of those different reservoirs, this will have a different impact on the atmospheric signal. And the first idea to use these records is not to use a very complex model, but simply consider mass balance. So the idea is that the total carbon in the system and the total carbon-13 in the system is constant, and we have some fractionation factors, and we simply solve the budget equations for CO₂ and for C13 to diagnose the two unknown fluxes between the land and the atmosphere, and between the ocean and the atmosphere, using a very simple reduced form model. To actually do this mass balance calculation, we have to underlie some fundamental hypotheses. And the first hypothesis that we want to address is those of that the whole changes are simply driven by changes in the land biosphere. So all the action is in the land biosphere, and the ocean is basically sitting there as a constant reservoir and reacting to the perturbation in a passive way. So that's actually the corresponding to Bill Rudimann's hypothesis that human land use drives the CO₂ increase in the Holocene. The results of this is we diagnose then delta C13 and compare it with the record, and what you can see is the diagnosed signal is really at odds with the reconstruction. And the conclusion then is terrestrial carbon release alone can certainly not be the dominant factor for the late Holocene CO₂ increase, as clearly outruled by the C13 record here. So other hypothesis needs to be tested, and I just will present here the one that we prefer, and that's a combination from land biosphere processes and also changes in the marine calcium carbonate cycle. And the changes in the marine calcium carbonate cycle may involve ocean sediment interactions, such as carbonate compensation in response to earlier uptake, or changes in calcite production, or they may involve changes in coral reef growth. Those processes are not isotopically distinguishable. And if we underlie this hypothesis, we can then come up with a terrestrial uptake that is shown here. We infer a terrestrial uptake of order 300 gigatons of carbon in the early Holocene, and then a slight release during the late Holocene. And as the atmospheric change is relatively small, this implies also a comparable flux from the ocean. So the mass balance gives us some hint about the magnitude of these fluxes, and we may now go a step further and ask ourselves, can we actually reproduce those fluxes now in a more complex process-based model? And can we really kind of estimate the atmospheric CO₂ signal when we, let's say, prescribe the land flux in a process-based ocean model? Or another part of the story is, of course, can we use a process-based land model to get to this carbon evolution as inferred from the mass balance approach? But here I will just focus on the ocean, we use here the Bern 3D model. That's a cost-efficient geostrophic frictional balance ocean model that can be used for paleo and probabilistic application. It includes many tracers, biogeochemical tracers, but also neodymium or protactinium thorium. It includes ocean sediments, and that's particularly important for the current work. And so it is well suited to actually also deal with this carbonate compensation process. To drive the model, we prescribe the following boundary conditions in this model. First, the Holocene land uptake, as inferred from the delta C13 mass balance. Then we need to make some assumption about how much the land carbon grew during the transition. There are delta C13 isotope data from the deep ocean that suggest a considerable increase in the land carbon storage over the transition. Basically, we consider two cases: no land carbon storage or an uptake of order 700 gigatons of carbon. And finally, a few years ago, there has been coral reef growth reconstructed by Wexey and Berger based on the sea level evolution and other evidence from coral reefs. So here are now these boundary conditions. The green line is just the Holocene land uptake from the delta C13 mass balance approach. So you see the 300 gigatons uptake in the early Holocene and a slight release thereafter. Then if we add to this the uptake during the transition, let's say of 700 gigatons of carbon, then we have simply assumed the carbon uptake is linear in time over this period of 6 kiloyear, and then in addition this 300 gigatons of carbon from the mass balance over the Holocene. And finally, this coral reef growth reconstruction from Wexey and Berger, which shows a peak here between 8 and 6 kiloyear before present in the coral reef growth, and relatively high reef growth during the recent millennium. And that's the results that we get with this model and all these drivers. We're pretty close to this record. That's quite surprising that we are getting so close, but perhaps that's also by chance. So what's more important is actually what are the mechanisms that actually lead to this agreement, and how could this play together. So obviously all the reconstructions that we prescribe in the boundary as boundary conditions have their uncertainties. So here is the coral reef growth mechanisms. This leads to a basically long-term increase with a pronounced spike here around 7 and 6 kiloyear. Now prescribing the land uptake in the early Holocene plus the coral reef growth leads us to this green line here, and you can see that actually the 300 gigatons carbon land uptake force the atmosphere to decline much stronger than is recorded in the data, and to increase here more than in the coral reef hypothesis, as we have carbonate compensation going on and also slight terrestrial release here. And now if we add the uptake during the transition, then we bring the green curve up here to the red, and from here as well. So these curves, of course, have their uncertainty. What's the key point here is that the CO₂ evolution, as we can see it recorded in the ice core, reflect a subtle balance between opposing natural processes. And so we need to get all these processes right to accurately get to the CO₂ evolution. But that seems to be possible, at least in some approximation. And we may also look at the other proxy record, and then I come to the end, Jerome. That is the carbonate ion concentration in the deep Pacific. Here is the model output. They show an increase in the concentration and then a decrease during the later part of the Holocene. And you see the decrease is roughly consistent with the estimates published by Bröcker based on his fragmentation index, that there is a late Holocene decrease in this carbonate ion concentration of 11 micromole per kilogram. And it's also consistent with suggestion by Anderson and Archer that there is a small LGM to pre-industrial change in the carbonate ion concentration. So the conclusion here is the Holocene CO₂ and C13 record can be quantitatively explained by a combination of natural factors. The atmospheric CO₂ reflects a delicate balance between different processes, and it's very unlikely that land use changes are responsible for the CO₂ changes that we observed. And I would like to thank you for the attention.
Thank you very much, Fortunat. We have time for 2 questions. Yes.
You showed in one of the diagrams that C13 is fractionated also by marine biota. So could it be that some unknown mechanism might also have changed global ocean productivity, which could have changed the C13 in the atmosphere that you have not considered in your scenarios?
Yes, that is a possibility, and actually we have for this mass balance calculations also postulated that the changes, the reconstructed changes in C13 and CO₂ are due to changes in land carbon storage in combination with changes in the marine organic carbon cycle, so to say, in changes in the delta C signature of surface ocean water due to changes in productivity or remineralization or whatever. And what we find are very large fluxes and of directly opposing nature, so that the ocean and the land flux are really very strongly anti-correlated and very large, and that's the reason why we consider that as relatively an unrealistic scenario. But it's also clear that we cannot firmly exclude it based on the data. And on the other side, it's also not clear how much actually the productivity could have changed over the Holocene based on the relatively small climate change during this period. But it's still a possibility that there is a contribution from the marine biological cycle to the observed evolution.
One more question, quick question. Right. I may have one maybe a bit provocative, but I heard from Hubertus Fischer that Bill Rudiman didn't really give up on the question of release of carbon from land use, saying that the buildup of peatlands could have actually compensated. So could you comment eventually on that?
Yes, I can comment on that. We actually also did simulations of, perhaps I may show this. Simulation of past land use with the LPJ model prescribing the height database, and what we end up is seeing very small signals in atmospheric CO₂. Let me perhaps show you this. How does this work here? Nope.
Yeah, you got
it. So this is the map from of human land use from the height database. So this is basically the current situation, and what is shown, the color indicates the fraction of land used by humans for agriculture, so cropland or pasture or cities. And you can see, okay, it's a heavily land use here in Europe and in North America and so on, also in South America here and in parts of South Africa or here in the tropics. And at 1700 the situation is already quite different. Land use is very strong here in Europe and also in parts of Asia, parts of Africa. But for example, in North America, it's a very little anthropogenic land use, simply as the white man wasn't really there yet. And if we go further back in time, then there are still a few centers. And we can prescribe these land use maps in the model and see what it does in CO₂. And the key map is actually here, because there's quite a bit of uncertainty how to scale this back in time. But anyway, the result is then, if we simply prescribe that in a dynamic global vegetation model, that we get really small signals in atmospheric CO₂ up to about 1700 of order 1 or 2 ppm. So even if we greatly underestimate, or if the land use maps greatly underestimate the land use, it's really hard to see how this can quantitatively come up to something like 20 ppm.